let's take the another example of construction of decoders, which is construct a 6 cross 4 construct a 4 cross 16, or let's say a 6 cross 64 decoder using 2 cross 4 decoders. So let's work out the steps to find the number of decoders required, the number of, let's say, 2 cross 4 decoders required to construct 6 cross 64 decoders. Okay, step 1, 6 cross 64 decoders can be written as 64 by 4. This 64 belongs to this, and this 4 belongs to 2 cross 4. So 64 divided by 4 gives 16, which can again be divided by 4, which gives 4, which can again be divided by 4, which gives 1. So this will be level 1, this will be level 2, this will be level 3. That is total number of 2 cross 4 decoders required for construction of 6 cross 64 is equal to this 16 plus this 4 plus this 1. So it gives total of 21 decoders required to construct 6 cross 4 decoders using 2 cross 4. Similarly, we can construct various kind of decoders. That is, we can also construct 6 cross 64 decoder by 5 cross 32. Let's work on one simple example to construct 6 cross 64 by 5 cross 32. 6 cross 64. Step 1. To find number of 5 cross 32 decoders required. This is decoders. 6 cross 64. We take this 64 here, and 5 cross 32. We take this 32 here. Okay. So 32 divided by 64, it gives 2. Now since this is not 1, we take again 32, and 32 divided by 32 send 2 divided by 32, which is less than 1, so we directly take it as 1. So the total number of 5 cross 32 decoders required to construct a 6 cross 64 decoders is 2 plus 1, which gives 3. Let's start up with the next topic, comparators. What are basically comparators? Also called as a magnitude comparators. Comparators are those circuits that compares the two numbers, and then they give the output corresponding to whether the number A is bigger or number 2 is bigger. So let's study the comparator, also called as a magnitude comparator. The types of comparator are 1-bit magnitude comparator, 2-bit magnitude comparators, and so on. Let's begin with a 1-bit magnitude comparator, which is as follows. The block diagram for 1-bit magnitude comparator can be roughly stated as N1, N2. This is Y1, Y2, Y3, Y4. Okay. Now these are the two numbers n1 and n2. There might be two possibilities. The first possibility is either n1 is greater than n2. Second is n1 less than n2. And the third possibility will be n1 is equal to n2. This is magnitude comparator. So let's say if n1 is greater than n2, we represent it as y1. y1, say n1 is greater than n2. Similarly, if n1 is equal to n2, let us represent it as y2. And if n1 is less than n2, we represent it as y3. Okay, so the truth table for 1 bit magnitude comparator, say n1, n2, 0, let's say 1, 1, 0, 1, 1. Let's say the corresponding output says y1, y2, y3. As we have denoted n1 greater than n2 by y1, n1 is equal to n2 by y2, and n1 less than n2 by y3. So let's see here. Now let's compare n1 by n2. n1 and 2 both are 0. That is, in this case n1 is equal to n2. So n1 is equal to n2 is represented by y2. So here correspondingly y2 will be high, rest will be 0. Similarly, n1 is equal to n2, that is n1 is less than n2, which is represented by y3. Therefore y3 will be high, y2 and y1 will be low. Now the third is n1 1, n2 0, that is n1 is greater than n2. Therefore y1 is high, y2 is low. Therefore y1 is high and rest order. And the last, n1 is equal to n2 again. Therefore y3 is high, y2 will be high as both are equal, and rest all will be 0. So this is the truth table for 2-bit magnitude comparator. Similarly, we can have a 3-bit magnitude comparator as well. Let's say a 2-bit magnitude comparator. The previous we studied was a 1-bit magnitude comparator. This is a 2-bit comparator. Here the comparator will be comparing 2 bits, n1 and n2, each having 2 bits, A, B, C, D. So let's start the numbering 0, 1, 2, 3, ... till we get 15. So the output again here will be the same kind, y1 for n1 greater than n2, which is for n1 greater than n2, y2 for n1 is equal to n2, and y3 for n1 less than n2. Okay, so let's compare now. Let's start the comparison. n1 is in this case 0, 0. That means n1 is equal to n2. So y2 will be 1, rest 0. Similarly, let's take this case. n1 is 0 and n2 is 1. That is n1 is less than n2. Therefore y3 1, 0. Similarly, for this case, n1 0, n2 2. That is n1 is less than n2 again. So n1 less than n2, that is y3 is 1, rest all 0. ... So if we move to this case 1 1, that is n1 is 1 1 3, and 2 is also 1 and 1 3, that is n1 is equal to n2, this 1 is 0. So if we take one more step, that is this 14. Okay, now let's consider this again. In this case, n1 is less than n2. Sorry, in this case n1 is 3, n2 is 2, that is n1 is greater than n2. So we take it here as y1 is 1 and rest all 0. Hence this is a 2-bit magnitude comparator truth table diagram. So that is, in general, if A is greater than B, we take it as logic 1, and if A is less than B, we take it as logic 0. Now if total 16 combinations are present, so the number of possible combinations for A greater than B will be 6. Number of possible combinations for A less than B will be 6, and number of possible combinations for A equal to B will be 4. This case is true for 2-bit magnitude comparators.